gamma 0 and gamma 1. Okay. And then there's one more condition, which is just purely a combinatorial condition. So let's call this involution bar. The combinatorial condition that sort of glues the graph and the involution together is the following. This is sort of a messy way to write it, but I sort of want to emphasize that the part of the world of subfactors and planar algebras, and we're just doing graph theory for a moment. So here, X denotes the multiset of neighbors. So what's this saying? You start with some vertex V on the graph, and take its dual vertex, and then take all of its neighbors, and then take all of their dual vertices, and then take all of their neighbors. You get the same thing as starting with a vertex, taking its neighbors, taking all the duals, taking all its neighbors, and taking the duals. And what on earth is that expressing? Back in the language of bimodules, with capital X, say, our favorite bimodule, this is just saying that X tensor A tensor X doesn't depend on how you emphasize. This is just expressing associativity of the fusion rules, in this particular case, tensor. Okay. And so this condition here is called the associativity. Okay. Now, the final thing to say, well, so what are we trying to do at this point? We're now trying to classify all of these graphs, so all graphs satisfying those conditions, up to some index limit. So remember, the index of one of these graphs is just the square of its largest value.